So I'm just going to kind of run through more Chapter 7 problems. Hopefully you guys have at least looked at that work set. So let's try this. Try to figure out a mechanism for that reaction. How does that reaction happen? And then what is the percent EE of the product?
Is there two methyls with the chlorine? Or is that a methyl with the chlorine, or is that a wet?
Here?
Yeah.
Yeah, so two methyls here. There's a methyl. Basically, the chlorine winds up here. I haven't put a wedge or a dash there. That's what I'm asking in the EE question. What do you get there? Yep.
This is a random question, but for leading groups, are the less heavy ones, like if I had a Cl on something, would that come off easier than Br?
No, it's actually the other way around.
Okay.
So iodide is it is really, I think, a weird. If you just memorize it, it's easy to memorize. Iodide is better than bromide, better than chloride, at both being a nucleophile and at being a leaving group. But it's a little weird that works out. You'd think the better leaving group would be a better nucleophile, and vice versa. It turns out that the chloride, bromide, and iodide are all about equally basic. They're all really weak bases. The carbon-iodide bond is a lot weaker, and that has to do. I can't remember where all I've said this. I know I've said it in a few places this semester, but you easily may not have heard it. So atoms of different size don't bond as strongly as atoms in the same size. All right, the analogy I always use with this is like shaking hands. All right, adults shake hands easily, right? Our hands are all, give or take, the same size, basically the same size. If you shake hands with a baby or a 2-year-old, I don't know if you've ever had to do this. But your hand is giant compared to their hand. There's not really, you as the strong adult can grip it really strongly, right? But if you try to shake hands with a baby the same way you shake hands with an adult, that's not going to be a good handshake. And atoms are really the same way. So iodide comes in here, right? And the orbital that's making the bond to the carbon is a 5-shell orbital. The orbitals and the carbon making a bond are second shell. So they're really wildly different sizes. And so they just don't overlap as well. And so a carbon-iodide bond is weaker than a carbon-bromide bond, it's weaker than a carbon-chloride bond. So it's easier for iodide to leave. And in nucleophilicity, it's polarizability, the same thing. The valence electrons are in the 5-shell, they're a long way, relatively farther away from the nucleus than the bromide. So iodide's a better nucleophile than bromide is a better nucleophile than chloride. But all of them do come off just fine. Take a couple of seconds to think about that. I'm going to go in the corner and have it be. Yeah, sorry.
This is kind of a more fundamental question, but when you take off the dash, why does it become axial? Is that just because of of the way the interactions are working?
Sorry.
Like the OH, that's a wedge, right?
Yeah.
When you take that off, what replaces it is axial and is not a wedge. Is that just because of the interactions of the molecule?
Well, I haven't actually indicated what the stereochemistry. I've drawn it with no stereochemistry. Hoping you guys will fill in the stereochemistry. So we'll have to think about that. See a couple of people writing. I'll give you another minute or two. Yeah.
The mechanism of this one, wouldn't you protonate the OH body?
Something. Yeah. So let's start with that. Like, do you have a leaving group in the carbon molecule?
Yeah.
What is it?
The hydroxide.
So hydroxide is never a leaving group. All right. So this is kind of a weird thing to. So OH minus is not going to be a leaving group in any of these. Chapter 7 reactions. All right. Hydroxide itself can't leave. It's too strong a base. So it's a really. You can easily draw up a reaction where thermodynamically hydroxide coming off would make sense. Like if you have a stronger base if your nucleophile is a stronger base than hydroxide, thermodynamically hydroxide might leave. But if the nucleophile is a stronger base than hydroxide, it's going to pull that proton off. And even if if the OH isn't a proton, if it's like an old methyl, it's just too strong a bond. That oxygen makes a really strong bond to carbon. Kinetically, it's not going to leave. So you got 3 different ways. Let me get these written out and I'll talk about them. All right, so there are 3 ways you can have OH act as a leaving group. I say OH in an SN1, SN2, E1, E2 reaction. The first way is to use thionyl chloride, SOCl2, to turn the OH into a chloride. So that reaction would be look like this. And the base can be sort of anything.
Now, isn't that the second option?
It is, yeah, thanks. I confused my head. So this OTS looks like this. All right, so you should know what TS is, capital T, little s. And you should know that if you've got this leaving group, an oxygen bonded to an SO2 and whatever else, that's going to act as a good leaving group. All right, the first option, sorry about getting these out of order, is to use SOCl2. I'm going to go ahead and put some stereochemistry in here. So if the chiral center, if the carbon with the OH is chiral, positive chloride won't change that, right? The reaction is the OH reacting with TS, so nothing happens here. In this reaction, we actually do get inversion. All right, so you actually wind up with end up with that intermediate and a chloride. You don't have to know the mechanism for this reaction, but you need to know that it inverts. All right, so if you have an OH, you treat it with SOCl2, the OH turns into a chloride, and the chiral center inverts.
Are these chapter 7 type reactions?
Yeah, I think both of these are in chapter. I mean, yeah, both of these reactions are going to be in chapter 7. Okay, so this is two-way. Now you've got a leaving group. You've turned that OH into a leaving group that can leave in any of these 4 reactions: SN1, SN2, E1, E2. The third way, which is the one in the reaction I asked you guys to process first, is to protonate the OH2, to protonate the OH. Okay, so when we do this, the only way to do this is to use a strong acid, right? And strong acid, not a base. Okay, so that OH, any alcohol OH is going to be a weak base, like water. Water is a weak base, so an alcohol is going to be a weak base. If you've got a neutral O with 2 covalent bonds, that O is going to be weakly basic. So if you treat a weak base with a strong acid, HCl is a strong acid, the reaction, the O is going to get protonated. Okay? So draw what you get from those 2 curved arrows.
Why is the arrow drawn from the oxygen to keep the hydrogen on? Okay, never mind.
Okay. Were you wanting to show the H moving?
Yeah, that's what I did.
Have you seen that before, or is that just like logically?
Just have it.
Okay. I mean, you've seen it before?
No.
Okay. No, sometimes people get this in high school chemistry. Not trying to insult high school chemistry teachers. But a lot of times, so there are 5 divisions of chemistry. Maybe I'll talk about this after exam 2, and we're talking about majors and stuff. But there's organic, inorganic, biochem, analytical, P-chem. And so I think there are probably a lot of high school chemistry teachers who are not organic chemists. And so what you were suggesting is that the arrow would show the H moving, so we would say this H is going to move to the O, and so we draw an arrow from the H to the O. That is a kind of some people just kind of come up with that on their own. Some people are taught that, and I suspect there are a lot of high school chemistry teachers. There might be non-organic chemistry professors here who would do that, because it does kind of make some sense. And so you have to think about what the arrow is showing. And we focus on atoms, but you should focus on electrons. All right, so the reason the arrow is drawn from the O to the H, if you look at charges, so we've got a lone pair, we've got 2 lone pairs on this oxygen. And so the arrow is showing the behavior, the movement of one of these lone pairs, and it's going toward that partial positive H. All right, so that first arrow shows the bond you want to show by drawing the arrow the other way. That first arrow makes a bond between the O and the H. Right? And then the second arrow is using the electrons and the sigma bond between H and Cl to put a lone pair on chloride. So I'm going to raise this up.
So that's just consistent with what we learned in chapter 3, right? You have a base attack.
Yeah,
so it's
yeah.
gonna be a-
Yeah, no, this is completely, this first step is completely a proton transfer Bronsted acid base. So it's an equilibrium. And again, nothing, right? There are no arrows to or from this chiral carbon. So it stays a wedge, right? If there's not an arrow to or from an atom in a mechanism, nothing happens to that mechanism. There should be no change on that. Right? None of the rest of this molecule is going to change. And we get chloride minus here. All right, so again, curved arrows in a mechanism show what electrons are doing. And there is a reason for that. So there are a lot of reactions where you could draw arrows the way a lot of you instinctively want to, which is showing atomic movement. Arrows from atoms to the atoms are going to bond. But that does fall apart. Then there are a lot of other reactions that won't explain reactions, the chemistry. If you focus on the electrons, and again, the electrons are the things that are shared in a bond. So if you keep track of where the electrons are, you'll keep track of bonds. Yeah.
Would there then be a third arrow?
Where's the third arrow?
The chlorine bond.
Oh yeah, we're not done yet.
Oh, okay.
Yeah. Sorry, we're not. This is not the. We're not to the end yet. All right. So I'm gonna redraw this. Put these H's out. All right. So yeah, the first step of this is we protonate the neutral oxygen. This reaction, HCl is a really strong acid, but so is this. This is a strong acid. So there's a rule of thumb here that you guys should internalize. And I'll get it written down. So mechanisms, reactions will either have, they don't have to have a strong acid or a strong base. There are plenty of reactions that don't have either of those, right? But a reaction can have a strong acid in it, or it can have a strong base in it, but it can't have both. Sort of by definition, strong acid is really reactive. A strong base is really reactive. If you have both a strong acid and a strong base in a reaction, they're going to react with each other. So if I say there's sulfuric acid in this reaction and there's hydroxide, whatever reaction I want to happen or think will happen isn't going to happen. The reaction will be hydroxide takes a proton from sulfuric acid, and I get water and hydrogen sulfate, and that's it. Nothing else happens. Now I don't have a strong acid or a base. All right, so as you draw these mechanisms, keep that in mind. So if you look at this reaction, we got HCl. I tell you there's HCl. So you've got a strong acid. Your mechanism then can't have a strong base. And that's another reason hydroxide can't leave, right? Hydroxide coming off would give you a strong base. Yeah.
Can a carbocation make something acidic?
Yes. Let me get to that. The next step then, and the slow step in this reaction, is water leaving. So water is a good leaving group. Generally speaking, weak bases are good leaving groups. So water is a good leaving group. But if you look at this, it's different. So HCl is a strong acid. Protonated water or protonated alcohol is a strong acid. So water leaving, water's a weak base. So water leaving is going to give you a carbocation. And we still got chloride hanging around, remember that. So the question you just asked, is a carbocation a strong acid? It is. It's not immediately clear how it's a strong acid, but that positive, remember there's a Lewis definition of acidity as well, which is a Lewis acid is an electron acceptor. So a positively charged carbon is seriously electron deficient. Carbon that doesn't have a full octet. Atoms without full, I think all of us tend to see positive formal charge the same. Positive carbon looks the same as a positive oxygen, right? So here's an oxygen, and it's positive, so we see that as the same as that positive carbon. But the positive oxygen actually has a full octet. It's got 8 electrons. It's got a formal positive charge, but it's got 8 electrons. The carbon has a formal positive charge, but it's only got 6 electrons. So it's actually more electron deficient than the oxygen. Okay, so that makes this a strong Lewis acid. The H's, the beta hydrogens here would be strong Bronsted acids. Okay, everybody good up to here? This is a secondary cation. And so you need to know, and if you look at this, if asking you to draw this mechanism, what's that?
Is this SN1 or SN2?
It's SN1,
Oh yeah, that's what I thought.
right? So you go,
And that would,
so you,
I don't want to ruin the fun, but would that mean that there's 0% EE?
yes, very good. So, right, we lose, as soon as this water comes off, we lose the stereochemistry. You get a carbocation, it's trigonal planar, it's flat, it's not chiral. So now anything else that comes on to bond to that can come from either side. But the other thing you got to look at here, and the tip-off that you have a cation in this reaction, is the carbon skeleton rearranges. This carbon here has 2 methyls on it. This carbon only has 1. In the product, this carbon has 2, that one has 1. So the carbon skeleton rearranges, and that is, at this point in your lives, a dead certainty that you have to have a carbocation. Yeah.
So I don't understand how it's a secondary cation because it only has like one group besides the hydrogen.
It's got 2 groups beside the hydrogen.
Oh.
Right? This way? No. Right? Yeah. So, put that over here. So we've got, you could have a methyl cation. So this is just methyl, right? You could have a primary, so the carbocation has 1 group other than hydrogen, so it would have 2 hydrogens there. You could have a secondary, and you could have a tertiary. Tertiary cation is more stable. Methyl cation is less stable. And actually, a methyl carbocation essentially cannot form. Like, it can. There are ways to do it, but it's really weird chemistry that you're not going to see under normal circumstances. Primary carbocations are really, really unstable themselves. Now, so there's kind of a line there between, you guys really shouldn't be making primary carbocations either. They can happen in solution, but they're rare. Secondary carbocations form slowly, but they do form. Tertiary carbocations are relatively stable. Again, more and less, this is all a relative thing. Okay, so when I say a tertiary carbocation is stable or more stable, I don't mean it's stable. Right? You would never make T-butyl cation and put it in a bottle and just leave it alone. It's gonna, every one of those cations is a really strong Lewis acid and highly reactive. The tertiary is more stable and the secondary is more stable than the primary. Yep.
If you were to add like an additional methyl to the original,
So here?
yeah, would that change which one's the slow step because you're creating a tertiary carbocation?
No, actually forming the carbocation is still going to be the slow step. Yeah.
Would you then do E1 rather than SN1 if there was an extra?
No, not necessarily. Let's get through this, and then I'll do what you want. I'll put a methyl on there, and we'll talk about it. The other thing I didn't put here is temperature. Right? So this is kind of a time to talk about like what. So this is a mechanism question. What I'm telling you is you did this reaction, you took this compound, you treated it with HCl, you've got this compound. Can you draw a mechanism that accounts for that product? So I'm telling you what the product is. On those kind of questions, you don't have to consider, is it going to be SN2 or E2? I mean, you have to figure out what the mechanism is. So thinking about SN1, E1, that sort of stuff. But it's clearly, right, this is a substitution. We've lost an OH, we've put a chloride in, so that's a substitution. You don't have a strong nucleophile, so it's a lot more likely to be SN1 than SN2. And again, because the carbons rearrange, because the skeleton of the molecule rearranges, the chloride comes on a different carbon than the OH leaves. That, for the reason I'm about to show you, is like, tells you absolutely this had to be involve a carbocation. And then, like you said, if it involves a carbocation, the EE is 0.
Okay. So if you like, on the on like an exam, if you were to ask us basically that same question with percent EE and then draw the mechanism as well, like that, what you have written up on the top is like perfect. Or satisfactory.
Like, well, if I was, like, I haven't finished the mechanism yet.
Oh, okay.
Yeah, the mechanism, this is the long mechanism. So, but I would give you, if I'm going to ask you a mechanism, if I'm going to ask you to draw a mechanism on the exam, I'm going to give you the starting material and the product and all the reagents. All right, so the other thing, the other common mistake I see people make is that you'd see this and you're like, well, there must be water there, or there must be alcohol, there must be something else there. It's possible I screwed up, and if you're really convinced I left something out, you should ask me. But in general, don't ever add stuff that I didn't say was there. Unless I'm asking you, like, how would you do this reaction? Then you can sort of put stuff in. But there are going to be, if you look on old exams, there are kind of two fundamental questions. Here's a reaction. Here's a starting material and a bunch of reagents. What's the product? Again, you don't want to be adding reagents because that changes what the I mean, maybe with the reagent you put in, your product's right, but that's not what I asked you. Likewise, on a mechanism, right, I'm giving you everything you need to draw this. So you don't need to know the temperature here because I'm telling you this got made. Now, if I was asking for a product, you'd really need to know what the temperature was. Because you could do, if the temperature's higher, you might do E1. All right, let me change out the... So if you're at home, finish this mechanism.